Hello everyone. Thank you, Andre, for the introduction. So as Andre was saying, we will talk about multidimensional linear attack and truncated differential attacks in the context of decorrelation theory. So first, during this talk, I will define the encryption as a block cipher, which is a permutation over L bits. And among the different attacks we will talk during this presentation, we will focus on linear cryptanalysis, where it's a statistical attack which take advantage of relation between plain text and ciphertext bits. If we denote by alpha and beta, two linear masks of L bits, we denote the correlation of the linear approximation as the difference between the probability that this linear approximation is equal to 0 and the probability that the linear approximation is equal to 1. During this talk, we will always talk about square correlation, and we denote by LP this square correlation for vector V of size 2b bits, which correspond to the input and output masks. Among the different generalization of linear cryptanalysis during this presentation, we focus on the multidimensional linear attack, which was introduced by Mia Ermelin and its co-author in 2008. For this attack, instead of dealing with one linear approximation, we deal with many linear approximations which span into a linear space V. And we will denote by K the dimension of this linear space. To be able to distinguish a cipher from a random permutation, we often use a capacity which corresponds to the sum of the square correlation of all the linear approximation involved in the attack. Another large family of statistical attack is differential cryptanalysis. For this attack, we have an input difference delta and output difference gamma, and we define the differential probability as the probability that if we have two plain text, x and x plus delta, then the encryption of the plain text is equal to a given gamma. And among the different generalization of this attack, we focus during this presentation on truncated differential attacks. Here, instead of having only one differences, as for multidimensional linear attack, we have a set of differences which span into a vector space, which for the purpose of this presentation will be the orthogonal of the vector space V used in linear attacks. And while the probability of a truncated differential is not usually computed as such, we will see that here we define the probability of a special truncated differential distinguisher as such, where we take two random plain texts, x and n prime, and we check if the difference x plus x prime and the encryption of x and the encryption of x prime is in the linear space orthogonal of V. So for the one which are not familiar with the context of decorrelation theory, I present here what we call an iterated distinguisher in this context. So the iterated distinguisher is a distinguisher with n iteration, where at each iteration we pick a sample, a set of d plain text, and from the ciphertext xy, we compute a Boolean value bi from a random given Boolean function t. And after all this n step of encryption, we compute a decision. Depending on a decision function f, we manage to decide if the cipher is random or not. Don't be afraid with all this notation. I will give some example just later on. So as I was saying, as we are in the context of statistical attack, we have to decide if the cipher is drawn as a random or if it's a permutation fixed by a random key. So depending on the context, we will denote C star when the encryption function it's a random permutation, or CK in the other case. We say that the cipher is decorrelated of order E if the infinite norm if this infinite norm is small. In 2003, Serge-Volneyev shows that for an iterated attack of order D, we have that the advantage of such distinguisher, so the advantage corresponds to this quantity, is bounded by this big value, which means that an iterated attack of order D has a small advantage if the cipher is decorated of order 2D, according to this bound, or smaller. So as an example, I want to show you the linear distinguisher for this attack. At each iteration, we only pick one plain text uniformly. We compute the encryption of this plain text, and we set this Boolean function bi as such. As at each iteration, there is only one plain text which is encrypted. We can say that it's a non-adapted iterated attack of order 1. In 2003, Serge-Volneyev shows that such distinguisher have the advantage of such distinguisher is bounded by this value. In the paper, we managed to improve the value of this bound using the Jensen inequality, and we show actually that this third root is now just a square root, and the factor 3 become a factor 2. Another example is differential cryptanalysis, and for this attack, at each iteration, we pick of the attack, we pick two plain texts with a given difference delta. So in that case, we can say that a differential attack it's a non-adaptive iterated attack of order 2. In 2003, Serge-Volneyev shows that for the function f, which corresponds to the max of the bi, the decision function f, we have that the advantage of the distinguisher is bounded by this value. And in the paper, actually, we managed to show that this bound is now independent of the decision function f. So to resume on what we know about the decorrelation order of the different statistical attacks, I will say that I will focus on the differential linear and boomerang attack, which have been studied in the thesis of Ashley Bay. And in particular, she shows that a cipher had to be decorated of order 4 to protect against differential linear and boomerang attack. Actually, in the paper, we managed to improve the bound using the Jensen inequality, as we have done for the linear cryptanalysis. And for boomerang attack, we now show that the bound is independent of the decision function f, as we have done for differential attacks. So now we focus on the main result of the paper. In particular, we have been studying multidimensional linear attack in the context of decorrelation theory. So such distinguisher is as such, where very similar to a linear distinguisher, except that for each linear approximation, we have a Boolean value Bij. It's also a non-adaptive iterated attack of order 1, and in the paper we show the following bound on the advantage of such attack. In the next couple of slides, I will present you some idea behind the proof of this quantity. So to provide such a bond, we have been considering a kind of special truncated differential distinguisher, which is not very practical, but will be very useful for the proof of that we needed for this paper. This special truncated differential distinguisher, it's a kind of non-plain text truncated differential distinguisher with only one sample. And the distinguisher is as such that we pick two plain text n and x prime at random, and we compute the encryption of these two plain text. And the decision function is equal to 1 if the difference between the plain text and the difference between the ciphertext is in the set that we wanted. Why did we want it where does come the idea to consider a special truncated differential distinguisher when we want to study multidimensional linear attacks? It's related to the link between differential cryptanalysis and linear cryptanalysis. In particular, in 1994, it has been shown that a differential probability can be computed from the square correlation of the cipher. And in 2014, we have generalized this link, and we show that the capacity of a multidimensional linear approximation involving linear mask in a vector space V is equal to the probability of a truncated differential involving differential in the space the orthogonal of V. From this observation and from this different relation between these different probability which are presented on this slide, we can actually manage to show that the advantage of a multidimensional linear distinguisher was bounded by this quantity. This bond tells us that this distinguisher is resistant up to 2 to the L minus Q divided by 2 queries, where L was the size of the cipher and Q was the dimension of the linear space. Nevertheless, we think that this bond can probably improve. And in particular, we think that we are losing a factor square root of n when iterating the attack, but we really did not manage to do better, in particular when not kind of fixing any, when giving some freedom to the decision function f. So now that we have used a kind of special truncated differential distinguisher to prove that the cipher decorated of order 2 it's enough to protect against multidimensional linear attack, we were also studying truncated differential attack in practice. For the purpose of this attack, we really have to divide the vector space V into a vector space V in and V out, where the difference delta and gamma are actually in the orthogonal of V in and in the orthogonal of V out. And if we denote by S the dimension of the set V in. The truncated differential distinguisher we study in the paper is as such, where at each iteration we pick two plain text with difference in the input space of difference. And so for such distinguisher, it's a non-adaptative iterated distinguisher of order 2. And using the result we have been provided for a special truncated differential distinguisher, we managed to show that the advantage of a truncated differential distinguisher is bounded by this value, which means that if the attacker have access to 2 to the L minus n minus 1 messages, the cipher decorated of order 2, it's enough to protect against truncated differential attacks. Nevertheless, for some special parameter S and Q, where Q is the dimension of the out, we have that the truncated differential attacks is equivalent to a differential linear attack. And last year, Ashley have shown that the decorrelation of order 4 is needed to protect against differential linear attacks. So, which means that decorrelation, a cipher decorated of order 4 or of order 2 might not be enough to protect against all kind of truncated differential attacks, but it protects against some truncated differential attacks. And in particular, the decorrelation of order 2 is correct for a small value of S. So to conclude during this talk, we have improved the bond for linear and differential linear distinguisher. We generalize the result about for differential and boomerang attacks. In particular now, it works for any decision function f. And we have been proving the security for multidimensional linear and truncated differential linear attack by decorrelation. Thank you.
Thank you, Celine, for the nice talk. Are there any questions? Okay, I do have a question. So there is this result that, for instance, the differential linear attack corresponds to order 4 of decorrelation,
yes.
And also the boomerang, also corresponds to order 4. Have you tried to reverse the question and ask yourself the question of, what are the higher orders beyond 4 in the decorrelation to which attacks they might correspond?
So actually, Ashley during her thesis have actually shown that 4 was exact number for boomerang and differential linear attack. That you really need the number 4 for both attacks.
Yeah, maybe there are some other attacks that correspond to higher orders of decorrelation.
Yes.
Like maybe there are some new attacks that correspond to high orders of decorrelation. Yeah.
Yeah.
That was the question. So if it's possible to reverse the question in this sense, I mean, to maybe come up with some other attacks that we don't know.
Yeah, there is attacks which require decorrelation order of 4. Higher order.
Okay,
4
higher
or
order.
even 5, 6.
Yeah.
It's have to be studied. Yeah.
Yes, exactly. Okay, good.
More you protect your cipher, more if you have a cipher decorated of order 6, you kind of expect it's protected against all the attacks we know, because those are the attack we know, it's 2 or 4 usually, but it also can also be protected against other attacks, but we don't know the attacks.
Okay. Yeah, there's another question.
What?
So the question is, how can you calculate this order for some real-world ciphers?
So actually, there have been some ciphers which have been designed so that you can compute the decorrelation order of these ciphers. But for ciphers that we design usually, classically, we cannot compute the decorrelation order easily. But there have been a lot of paper, DLC for cipher, and many paper, like a cipher which is called Coconuts, for instance, for which they have been designed to be protected of decorrelation order 4, or I don't remember the number for all this cipher, but there have been cipher which have been designed to have a proof of security in this context.
Thank you. More questions? Okay, then we will switch to the next talk.